So, we were discussing dimensional analysis and dimensionless groups. In any problem, there will be one dependent dimensionless group that has to be determined and a series of independent dimensionless groups. I am sorry, there will be one dependent dimensional parameter that has to be determined and a series of independent dimensional parameters. If there are a total of n such parameters and if all of these contain a total of m dimensions, then there are n minus m dimensionless groups, out of which one is the dependent dimensionless group and the rest of them are independent dimensionless groups. So, I had illustrated this for you in the last class by considering a particle settling in a fluid, where we had wanted to calculate what is the drag force exerted by the fluid on the particle. Okay. So, the mass times the acceleration of the particle is the sum of the gravitational force, the buoyancy force and the drag force. The drag force is due to the flow of the fluid around the particle, the frictional force exerted by the fluid on the particle, which results in a net drag force on the particle. This drag force depends the fluid properties, the particle diameter and the particle velocity and the fluid properties, that is the density and the viscosity. And based upon dimensional analysis, we had got a relation between two dimensionless groups. Okay. That is the drag force scaled by either viscous or inertial scales, and a dimensionless group called the Reynolds number, which is the ratio of inertial and viscous effects. And I told you the drag force can be scaled either by inertia or by viscosity. When the Reynolds number is small, viscosity is dominant and therefore inertia will not be significant, and therefore the drag force is purely viscous and it is appropriate to use the viscous scaling for the drag force. At high Reynolds number, the inertia is dominant and it is appropriate to use inertial scaling, that is containing the density. And I had also defined for you the drag coefficient, which is the drag force divided by the projected area scaled by the kinetic energy per unit volume. Okay. And I had related to the inertial scaling of the drag force. We had also calculated other quantities, Brownian diffusion for example of a colloidal particle in a fluid, the distance travelled on average due to the Brownian motion due to the force exerted by the molecules on small particles, size 1 micron or less. The force on average is 0, so the displacement on average is 0. However, the square of the displacement is non-zero, and in Brownian motion the square of the displacement increases proportional to time. That is, displacement squared divided by time is a constant, and that constant is proportional to the Brownian diffusion coefficient. And that Brownian diffusion coefficient depends upon the molecular fluctuating velocities, because it is this molecular motion that is causing the fluctuations in the particle velocity. And these velocities are dampened by the frictional effects, by drag force. And that drag force for these small particles, recall Reynolds number is rho v d by mu. So, when diameter is very small, the Reynolds number is small, the force is dominated by viscosity, and therefore inertia is not a factor. And based upon that, we had got an expression for the Brownian diffusion coefficient to within a multiplicative constant just by dimensional analysis. Okay. And I had also solved some problems for calculating the torque on a rotating particle for you. Okay. So, now we will go on to calculating quantities of interest in transport phenomena, the use of dimensional analysis for deriving dimensionless groups for quantities of interest in transport phenomena. The first example we will take is mass transfer. From a particle. Okay. I will assume that we have a particle of diameter d, okay, moving with some velocity v in some direction, okay, and this particle, it's, let us assume it is a solute particle, and the solute concentration far from the particle is C infinity, and the solute concentration at the surface of the particle, I will call it as the solute concentration at the surface of the particle, I will call it as Cs. Okay. Now, why is this mass transport taking place? Okay. If I magnify a small zone somewhere, okay, on the surface of the particle, this is the particle, okay, and you have some fluid flow because the particle is moving in some manner relative to the fluid. Okay. So, there is some velocity profile in the fluid. Okay. The velocity relative to the fluid far away, let us assume that the fluid far away is at 0 velocity, it is stationary. Then there is a velocity of the particle of the fluid close to the particle, because the particle is moving relative to the fluid. Okay. And there is also diffusion, okay, of solute either from or to the particle depending upon the concentration difference. Okay. There is diffusion at the surface of the particle. Note that convection transports particle along the fluid flow. Okay. So, at the surface there is no fluid flow perpendicular to the surface, therefore, there is no convection perpendicular to the surface. Therefore, transport across the surface has to take place entirely due to diffusion. Okay. So, basically as the particle moves along, there is convective transport, that the fluid carries the solute along with it, and at the surface that transport has to take place due to diffusion. Okay. So, that is the physical mechanism. Okay. So, what are the parameters that we want to calculate? Okay. Obviously, we would like to know what is the total flux of mass from the surface, because that basically determines how much is dissolving into the fluid or how much is precipitating out of the fluid into the onto the particle. Okay. So, we would like to know what is the total mass transported per unit time from the particle surface. Correlations are not usually written for the total mass transported, because that depends upon the surface area. So, in a sense that is an extensive quantity. Correlations are usually written for an intensive quantity, which is the average flux. JAV, which is the mass transported per unit area per unit time of the particle surface. So, that is the dependent quantity. Okay. The dependent quantity is the average flux JAV, which is the mass transported per unit area per unit time, and you would multiply this flux by the total surface area to get the total mass that is transported per unit time. Okay. So, that would tell you the rate at which the solute is either dissolving or precipitating onto the particle surface. Okay. So, the correlation are written for the average flux, an intensive quantity, mass transported per unit area per unit time. Okay. Mass transported per unit area per unit time. Okay. So, that is what the correlations are usually written for this dependent variable. What are the independent variables in this case? Okay. Okay. Obviously, first one is the concentration difference. Delta C is equal to the surface concentration minus the concentration far from the surface. Okay. Concentration is mass per unit volume. Okay, so let me just write this. Flux is mass per unit area per unit time. solvent the concentration is mass per unit volume. Okay, it has dimensions of m L power minus 3. The transport due to the concentration diffusion concentration difference is due to diffusion. So, obviously, the diffusion coefficient is a parameter. D, the diffusion coefficient D is a parameter, and that diffusion coefficient has dimensions of length square T inverse as we calculated when we did dimensional analysis. Okay. And of course, the particle diameter D also has to be a parameter. It has dimensions of length. Now, transport is taking place due to diffusion at the surface, but within the fluid the transport is taking place due to convection. Convective transport depends upon the details of the velocity field. Okay. So, therefore, the fluid properties as well as the flow velocity, all of them are independent parameters. Okay. So, the other independent parameters are the velocity V, which is mass length per unit time, the density rho m L power minus 3, and the viscosity mu, which is m L inverse T inverse. So, these are the parameters, independent and dependent parameters. So, you have one dependent parameter, the flux, and a total of 5 independent parameters, 6 independent parameters. Okay. 6 independent parameters, 1 dependent parameter, total of 7 parameters. How many dimensions? 3 dimensions, okay, mass, length and time. Okay. Therefore, I should have 4 dimensionless groups. Okay. Therefore, I should have 4 dimensionless groups. I can, however, make a simplification if the mass, the concentration does not affect the fluid properties. Okay. Note that concentration is mass of solute per unit volume. The fluid density is total mass, that is solute plus solvent per unit volume. Okay. If the variation in concentration does not affect the fluid properties, specifically the density, then I can consider the solute mass and the total mass as 2 independent quantities. Okay. The solute mass affects only the properties relating to mass transfer, that is the flux and the concentration difference. The total mass affects the properties relating to the fluid flow, that is the density and the viscosity. Okay. So, therefore, I can make a distinction between solute mass and total mass, okay, if the solute mass does not affect the fluid properties. Okay. In that case, my flux depends upon the solute mass and the concentration depends upon the solute mass. Okay. The density and the viscosity depend upon the total mass. Okay. So, there is a distinction between the solute mass and the total mass. In this case, there are 4 dimensions. Even though solute mass and total mass are actually the same dimension, if there is no dependence of the fluid properties on the concentration, okay, if I can assume the density and viscosity do not depend upon the concentration, I can make a distinction between the solute mass and the total mass. In that case, I have 4 dimensions. Solute mass and total mass are different dimensions. And in that case, I have 4 dimensions, 7 dimensional parameters, and therefore 3 dimensionless groups, out of which one is dependent and the other is independent. Okay. So, one of the dimensionless groups has to contain the average flux, and this has the solute mass in it. So, it is dependent upon the concentration difference, the diameter and the diffusion coefficient. Okay. So, this dependent dimensionless group it has the average flux, okay, and it should be dependent upon delta C per alpha, okay, d per beta and the diameter per gamma. Okay, so, that is the general expression. And of course, we could do dimensional analysis. On the left side you will have ms power 0, L power 0, T power 0. On the right side you put and substitute all the terms and then get the dependencies. Okay. So, that is one way to do it. A simpler way to do it is to actually get a relationship directly from a relation that we already know. Okay. We know that the Fick's law for diffusion is the flux locally, okay, is equal to minus d delta C by delta Z. Okay. That is, if we have diffusion taking place across a slab of fluid, okay, of thickness delta Z, and the difference in concentration, okay, across this was delta C. Okay, the difference in concentration was delta C. That means that the flux locally has to be equal to minus d times delta C by delta Z. This is a local relationship valid at each point in the flow. It does not valid for the entire system. However, the left and the right side of this equation have to have the same dimension because they have to be dimensionally consistent. Okay. So, therefore, I can get a dimensionless group by scaling the flux by a quantity which has the same dimension as the right hand side, which is d delta C by d. This will be dimensionless, okay, because the denominator has the same dimension as the right side of Fick's law for diffusion. Note that this Fick's law is not applicable for the entire system, it is applicable only locally at each point. However, both the left and the right sides have the same dimension. So, I can get a dimensionless group just by scaling it in this way. Okay. So, that is a dependent dimensionless group. Okay. It is called the Sherwood number. Okay. Okay, which is obtained by just using Fick's law for diffusion to scale the average flux by a quantity that has the same dimension as the right side of Fick's law. Okay. So, that is the dependent dimensionless group. Okay. A non-dimensional flux, okay, Sherwood number is a non-dimensional flux which is the dependent dimensionless group. What are the independent dimensionless groups? Okay. One of them we already calculated, the Reynolds number is equal to rho v d by mu, okay. And there is another dimensionless group, okay, and that has to involve the velocity and the diffusion coefficient. Note that the velocity has dimensions of length per time, diffusion coefficient has dimensions of length square per time. Okay. So, I can just construct a dimensionless group as velocity times diameter by the diffusion coefficient. This is dimensionless, okay, and this is what is called a Peclet number. Okay. So, the Sherwood number is the independent dimensionless group, the Reynolds and the Peclet number are the dependent dimensionless groups. Therefore, the correlation between these two will be necessarily of the form Sherwood number is equal to some function of Reynolds number and the Peclet number. Physically, what do these mean? Reynolds number, as I have already discussed, is the ratio of inertial and viscous effects. The Peclet number, velocity times diameter divided by diffusion coefficient. Velocity determines the convective rate of transport. The diffusion coefficient determines the diffusive rate of transport due to diffusion. Therefore, the Peclet number is a ratio in this case, okay, of mass convection by diffusion. Okay, the Peclet number is the ratio of mass convection by mass diffusion. The Reynolds number is the ratio of inertia by viscosity. I will also show you later that this can be interpreted as momentum diffusion by momentum convection. Okay. So, this is the form of the correlation between the Sherwood number, the Reynolds number and the Peclet number. Let us look at limiting cases. Okay. If we take the limit Pe much smaller than 1, that means that convective transport is negligible compared to diffusive transport. Okay. That means that convective transport is negligible compared to diffusive transport. In this case, the convective velocity should not be a parameter at all in determining the average transport rate. Okay. So, the velocity should not be a parameter at all in determining the average transport rate. If the velocity is not important, then the Reynolds number is also not important, because the Reynolds number tells you the ratio of inertia and viscosity that determines that velocity field. And so, if velocity is not important, then the ratio of inertia, then the Reynolds number is also not important. In this case, velocity is no longer a parameter, and therefore, the Sherwood number has to be equal to a constant. Okay. In the limit of Peclet number becoming very small, the Sherwood number has to tend to a constant. What that constant is, we cannot calculate using dimensional analysis alone. We will be able to calculate it later in the course, what the value of the constant is by actually solving for the concentration field. It turns out that for a spherical particle, this constant is just equal to 2. Okay. So, therefore, in the limit of small Peclet number, the Sherwood number is independent of the Peclet number and it tends to a constant value. That constant is equal to 2 in the limit of low Reynolds number. What about in the limit of Peclet number much greater than 1? Okay. It means that convective transport is dominant compared to diffusive transport. Okay. And simplistically, you would think that you can just neglect diffusion altogether and just calculate the transport rates by considering convection alone. Turns out that that is not correct. The reason is the following. Okay. You can see from this picture that convection only transports mass along the velocity. Okay. Convection transports mass only along the velocity. At the surface of a solid particle, the velocity perpendicular to the surface is equal to 0. Okay. Therefore, there is no velocity perpendicular to the surface. That means that there cannot be any transport perpendicular to the surface due to convection. Okay. So, even when convection is dominant, the Peclet number is large, okay, the transport in most of the fluid domain will occur due to convection. However, transport at the surface, across the surface, cannot take place due to convection, because there is no velocity perpendicular to the surface. Therefore, transport across the surface has to take place only due to diffusion. Okay. And therefore, the Peclet number is the Prandtl number, the Sherwood number is a function of Reynolds number and Peclet number, even in the limit of high Peclet number. Okay. You cannot neglect diffusion. Okay. You will have a balance between convection and diffusion close to the surface, convection along the surface and diffusion perpendicular to the surface, and this balance is what will determine the rate of transport across the surface. Okay. So, in the limit Peclet number due to 1, you cannot neglect diffusion. Okay, because diffusion across the surface has to ultimately happen due to, because transport across the surface has to ultimately happen due to diffusion. Okay. And that diffusive transport is what results in transport to or from the particle. Okay. Okay. Now, this analysis can be extended quite easily to, for example, the drying of particles. in problems where you have a wet particle which is drying due to the dry air outside, right, there is moisture that is evaporating from the surface, and the evaporation takes place because of the difference in concentration, the saturation concentration at the particle surface and the concentration far away. Okay, that is, this is the relative humidity, okay, compared to that in the ambient air. Okay. And usually these in these problems these are expressed in terms of the partial pressure of water far away and the partial pressure of water at the surface. Okay, saturation water partial saturated the pressure the saturation pressure of water at the particle surface, which is only a function of temperature. Okay. Okay. So, therefore, this difference in the vapor pressure of water at the surface, the vapor pressure is only a function of the temperature, and the partial pressure of water far away, that is what acts as a driving force for the diffusive transport. Okay. And we can easily convert this into a Sherwood number correlation just by realizing that the concentration. Okay, so, let me molar concentration okay, or molecular number of molecules per unit volume or number of moles per unit volume. Okay. Let me write this in terms of the okay. The number density is equal to P by kT, number of molecules per unit volume. This is from ideal gas law. Okay. Number of molecules per unit volume is P by kT, number of moles per unit volume is P by RT. Okay. So, there is a number density, number of molecules per unit volume. Okay. The concentration is equal to the number of moles per unit volume times the molecular weight. Okay. Number of molecules per unit volume times the weight of one molecule, number of moles per unit volume times the weight of one mole. Okay. Either of those can be used. If you are using in terms of molecules, the Boltzmann constant; in terms of moles, the ideal gas constant. Okay. Either of those. Okay. So, that is the concentration C. Okay. So, this is equal to P times the mass divided by kBT, where mW is the mass of a molecule. If I were to use the ideal gas constant, it would be the mass of one mole. Okay. Therefore, delta C is equal to C surface minus C infinity is going to be equal to mW by kBT into the pressure, saturation pressure, minus the pressure in the ambient. Okay, the saturation pressure minus the pressure in the ambient. So, that is delta C. Okay. And then the Sherwood number would be defined as J average by D delta C by D, which is the same as J average by D into mW by kT into the diameter. Okay. So, that is how you would use it in case the concentration is not specified, but rather the vapor pressure and the partial pressure. The vapor pressure at the surface, the saturation vapor pressure at the surface, and the partial pressure of water far away. In case those are satisfied, you can use the ideal gas law in order to express the Sherwood number in a similar manner. Okay. So, I have got I have determined from dimensional analysis a relation between dimensionless groups. Dimensional analysis and one additional input, and that is that there is no interconversion between the mass of solute and the fluid mass, that is, the change in concentration does not affect the fluid properties. This, of course, is an approximation. If the change in solute concentration affects the fluid properties, that has to be incorporated in this. If the change in solute concentration does not affect the fluid properties, there are 4 dimensions: solute mass, total mass, length and time. 7 parameters: dependent parameter average flux, independent parameter concentration difference, diffusion, diameter, velocity and the fluid properties. And based upon that, we had got a relation between the dependent dimensionless group, the Sherwood number, which is a dimensionless flux, and the independent dimensionless groups, 2 numbers: Reynolds number, ratio of inertia and viscosity in the fluid; Peclet number, ratio of mass convection and mass diffusion. In the limit of small Peclet number, convection is not important. Transport is entirely due to diffusion. Velocity is not a parameter. Therefore, the Sherwood number has got to be equal to a constant. High Peclet number, you might naively think that diffusion can be neglected, but that is not so, because even though convection can transport mass along the particle surface, it cannot transport mass across the surface, because the flow velocity perpendicular to the surface is 0. Therefore, the diffusion is an important parameter even when the Peclet number is large, and that has to be included in the correlations. I will go on to discussing a similar problem in heat transfer, the heat transfer in a heat exchanger, in the next lecture. So, I will continue then.